When I first ordered an Arduino NANO RP2040 Connect, I was excited to see that Arduino was promising support for MicroPython. It wasn't available when I first got the Arduino, so I used C++ in my current project, but it's out now, so I thought I'd give it a try. In this video, I'm going to look at what MicroPython is, how it is implemented on the Arduino, and is it actually any good? If you can't wait to get started, you can skip to a later chapter when I explain how to install the IDE. But first, I'm going to give you a bit of an explanation about the Arduino boards and their support for MicroPython. Arduino has traditionally used C++ for programming the appropriate controller. There have been unofficial versions of Python that have been available for some models, including MicroPython and CircuitPython, which is Adafruit's version of MicroPython. This is the first time that Arduino have officially created a port of Python, and they've used MicroPython. They've made some unusual choices in how this is implemented, which I'll explain later in the video. Arduino only provides support for 4 models at the moment. These are the Arduino Nano BLE and the Arduino Nano BLE Sense, the Arduino Nano RP2040 Connect, and the Arduino Pro Portenta H7. There is a different number of examples for these, with the Portenta having significantly more examples available for it. I'm going to be concentrating here on the Arduino Nano RP2040 Connect. This is the Arduino based around the RP2040 microcontroller from Raspberry Pi. It is similar to the Raspberry Pi Pico, but with a smaller size and lots more features. I've already covered more details about the board in another video. Traditionally, the Arduino boards are programmed in C or C++. This has a reputation of being difficult to program. I'd argue that that's not necessarily the case on the Arduino, but I'd also say that Python is probably a little easier, and it's commonly used as a beginner's language. It makes the Arduino easier for beginners. One thing about Python is that it's an interpreted language. But what does that mean? The thing about microcontrollers and computers is that they cannot actually run code that is developed using a high-level programming language directly on the hardware. The code that is written first needs to be converted into instructions that the microcontroller can understand. There are essentially 2 ways of doing this. These are based around programs that are compiled or interpreted. Actually, there are some other options, but this is simplified to keep it easier to understand. Traditional programming languages, such as C and C++, are normally compiled. This means you send your code to a compiler, which converts this into the raw machine code, and then that can be run directly on the microcontroller. Python is instead an interpreted language. Instead of being compiled in advance, the code is read whilst the program is running and is converted to computer instructions. This needs the interpreter to be installed on the microcontroller. There are advantages and disadvantages to both. One of the main advantages of a compiled language is performance, as it can run directly. An advantage to an interpreted language is portability across different platforms without needing to recompile the program first. When it comes to an Arduino, then an additional disadvantage of using an interpreted language is that you first need to install the interpreter, which is where MicroPython comes in. The regular Python interpreter is about 30 megabytes in size and needs a significant amount of memory to run. This is without including the modules. It's too much of an overhead to use on an Arduino microcontroller. MicroPython is based around the same programming language used in Python, but it's stripped down to fit into less than 1 megabytes of space, and so that it needs much less RAM. Whilst there are some changes that were made to MicroPython, it maintains most of the features that the full programming language uses and runs well on microcontrollers. I'm going to look at 2 ways of running MicroPython on the Arduino RP2040. The official Arduino way, as well as how you could use the standard MicroPython version using Thonny or using minicom and the command line. Both will work for the example I'm using. The first is based around the OpenMV fork of MicroPython, whereas the later example will use the upstream version directly from micropython.org. For the demonstration, I'll be using my NeoPixel board that I created. This is a PCB which has the Arduino Nano mounted on it and can then control RGB LED pixel strips, sometimes known as NeoPixels. The PCB was designed using KiCad and manufactured by JLC PCB. I've covered that in another video. I won't be trying to replicate my previous project, which creates a wireless NeoPixel server. For this, I'll just use it to turn a few LEDs on and off as a demonstration. I'm going to look here at installing and using MicroPython using OpenMV. OpenMV appears to be an odd choice for the Arduino, that it's really designed for a camera module or for machine vision. Because it's designed for cameras, its desktop IDE appears to be a bit unusual and some of the messages don't apply directly. It is covered in the setup instructions from Arduino and includes some example code, which is useful. To get started, first download the OpenMV IDE from the openmv.io website. There are versions for most common operating systems, including OS X, Ubuntu and the Raspberry Pi OS. I was hoping to demonstrate this next step using a Raspberry Pi, but unfortunately at the moment OpenMV is not compatible with the current version of Raspberry Pi OS based around Bullseye. This is a recent version of the Raspberry Pi OS, so you might expect that it will take a little while for that to catch up. However, it has also got issues with the older version using Buster, although I did find a workaround which I'll explain on my website linked in the description, but it's going to be clearer to demonstrate this using Ubuntu. So I'm going to show how to use OpenMV using Ubuntu, and when I come to the next stage showing Thonny and the official MicroPython from microcontroller.org, the upstream version, I'll use a Raspberry Pi for that. So when you download the Ubuntu file from OpenMV, it's an executable installer. You just give that permission using chmod +x to execute and then run the installer. Now that you've installed OpenMV, you can just launch it. It just comes up with this basic Hello World program. Now the next step is to install the MicroPython bootloader onto the Arduino. If you've not used the Arduino before, then potentially it'll automatically go into boot select mode. But if not, then or if you've put a program on before, you're going to have to change it into boot select mode. This is normally done by a double tap on the button on the top of the Arduino. If that doesn't work, then you may need to short together the reset and the ground pin when you power it on, and that will do the same. You can see that it's in boot select mode as it will have a device appear, RPI-RP2, which is a virtual file system. So after connecting that, if you use the connect button, which is the bottom left hand corner, it'll detect the board, but it'll see that it doesn't have the MicroPython version that we're wanting on. So you can just click OK to install the latest version, and then you can watch as this gets installed onto the flash. Click OK. Now there's some sample code that we can use. This hello world.py is irrelevant because this is for the cameras, and this is one of the things about this being designed for cameras. Really, it's not really that useful, but if we go into the examples, you'll see that under Arduino we've got quite a few examples depending on the board. So the BLE sends, the RP2040, and as you see the port enter has got a lot more options on, a lot more machine learning and things like that. But we're interested in the Nano RP2040, and we can try the most basic one if you just click on basics and Blinky. This is like the blink in the normal Arduinos. It's just going to flash the onboard LED. So if you just, once that's on, you'll see that we're connected on the bottom left hand corner, and you can press play, and that's going to download it to the Arduino and then set it running. And it's now blinking. There are a limited number of code examples at the moment, and the one thing I wanted to do was control NeoPixels. I'm not going to create a web-based pixel server. I've already done that in C++. See the link at the top of this video or in the description. It would be a big job to rewrite that now, but I will use a simple pixel light sequence as an example of how this can be done. I'm also using the PCB which I designed for the pixel server. The PCB was provided by JLC PCB, and I have another video explaining about how I designed that in KiCad. If you don't want to get the PCB made, you can use a breadboard or even connect the Arduino directly to the pixel strip, although there should really be a level shifter if running the pixels at 5 volt, which is what the PCB provides. The first hurdle is that there's no example code in OpenMV and no documentation available specifically for the Arduino RP2040. The Arduino is based around the RP2040, which is also used in the Raspberry Pi Pico. So I searched for the Pico, and there's a good chance that code designed for that would work as well. I was able to find the source code, which is currently being developed by GitHub user blaze-r. Here's the code you find, and you'll see there's a file called neopixel.py. When I've created code for MicroPython in the past, then I've often used Thonny, which allows you to save the code to the device. OpenMV allows you to transfer the current file, which is what's happening when pressing the play button, but not the other included files. You therefore need to transfer the NeoPixel file manually, which can be achieved using the standard file manager and looking for the file system 8.4 megabyte volume. So if I just show you in the file manager, I've got two files here. So neopixel.py is the file that I've downloaded from the GitHub site. The testpixels-omv is the file that I've created to create a demonstration. I'll show you that in a minute. So we just need to take this neopixels.py and drag and drop it onto this drive that says 8.4 megabytes volume. And now my own script can make use of that. So I'm going to open this into OpenMV. Let's just clear off the other ones. And this is the code that I've created. You can download this from my website, and I'll link to that in the description. Most of the code is self-explanatory. It uses the NeoPixel library. One thing to be aware of is this pin number. So the pin number has to be the GPIO reference, which in this case is 17, versus the Arduino reference, which is digital pin 5. Really, you just need to make sure that this relates to the GPIO pin on the RP2040. I've just defined some colours, set the brightness, and then I just got a loop that's going to turn 10 of the NeoPixels onto each of these colours in turn. And you can then just press play, reconnect. Just needed to reconnect there. Once the MicroPython interpreter is installed, you can just click connect whenever you need to connect. And then just click play, and it's running now. And now the LED strips are turning on a colour at a time. If you want the program to run automatically when the Arduino is powered on, then you need to save it as main.py, and it actually provides you as a way of doing that. So you can go to Tools, Save Open Script to OpenMV, as main.py. It doesn't matter whether you strip those or not, that just reduces the size of it. And then that will transfer it to the Arduino and name it main.py, so that now that is automatically run whenever it is started. Now I'm going to show you as well how you can use that with Thonny. So after you've installed using OpenMV, you can also switch to the Thonny editor if you prefer. So I've opened those same two files on here, and we need to connect to the device. So you select interpreter, so MicroPython generic and board in FS mode. We can now save these. If we just click stop, it's going to stop the interpreter running, so that was running from before. So the reason I said before, in Thonny you can save this file. You save as, it gives you the option to save it to the MicroPython device. There. Now you can do the same with that, or you can just run it from where it is and it'll transfer it over. And that's running. As you can see, it shows the serial console in the shell. You could also have viewed that in OpenMV. There is a shell option in there. I'm now going to show how you can use the upstream version of MicroPython. This is the version from micropython.org. It's designed for the Arduino RP2040, but is before the modifications that Arduino have made. I'm not sure what the differences are. It may mean there are libraries missing, but the code used in this example works fine on this. I've noticed one thing which is different, is that the version of micropython.org does not appear as a removable drive as with the OpenMV version. You can, however, save files using Thonny and using command line tools like ampy, so it's not a problem. So here I am using Raspberry Pi 4 with Raspberry Pi OS and its Bullseye. So on the MicroPython website, you just go to download and then find the Arduino NANO RP2040. There we go. And download the whichever version you want. I'm going to take the latest. This is on here. There may be a newer version. In fact, as these nightly builds, they'll most likely will be. And we can see that it's downloaded to downloads. Now, from before, I used the OpenMV version, so it's showing this 8.4 megabyte volume. And that's not what we want, so I need to double tap to go back into the blue select mode. That disappears, and hopefully we should get... No, I don't think I think it's difficult to tap it quite fast enough, or if you get the one that says 8 megabytes, that means that the MicroPython from OpenMV is running. This is the one we want, so we'll just cancel that. The RPI-RP2. So this means we're in boot select mode. Take that UF2 file that we've downloaded and just drag and drop it onto there. You can see that before that it just had these index.html and this info.txt. Then that's restarted it, so the menu's disappeared, and you'll notice that there's no longer a drive. So this is one of the downsides. It means you can't just drag and drop files onto the Arduino once you've installed MicroPython. Not a problem for the program files, but something you need to be aware of. If you're wanting to upload files, you'll have to use a command line tool, say, such as ampy. So I'm going to launch the Thonny Python IDE. and we can change here to MicroPython. It thinks it's a Pico, that's fine. So we're actually on here, we can run commands actually on the Arduino, and that's actually running on the Arduino, and the serial output's coming back. So I'm now going to add the two files that we had earlier. Now I'm just going to switch to the regular mode here. This is in a simplified mode. If we go into the regular mode, I'm going to have to relaunch that. Then you'll get the full menu options. And you can see we can select the interpreter here, and could use the Raspberry Pi Pico or MicroPython generic on here, and board in FS mode, that's the one we want, or it's the same as there. Now I'm going to open the file we had previously. So I've downloaded onto this computer the OpenMV version of the test pixels and the neopixel.py that we downloaded from the GitHub previously. Now there's one thing that doesn't appear to work here, in that this line here, what it's going to do is from neopixel, it's import neopixel. So it's from this file called neopixel.py, import the class neopixel. And normally you can just put those two in the same directory and it will find them. For some reason that didn't work when I tried to do that through Thonny. Instead you need to create a separate directory and explicitly say that directory. I don't know why that's the case. I might try and investigate that a bit further, but for now we need to save as and choose the MicroPython device, and we need to create a new directory. I'm going to call it lib, and I'm going to just save it in there called neopixel.py. And then I need to change this, and I'm going to call this test pixels dash mpy to indicate the upstream MicroPython version .py. Now if we need to tell it it's in that directory, so if you put from lib.neopixel, that works. Save that, and now we can see it's running. Now you can use the play and stop buttons on here, and I actually like this as an editor because it does give you that ability to save it direct to the Arduino. Another alternative to using OpenMV or the Thonny editor is that there's some command line tools you can use as well. To be able to interact with Python from the command line, you can use the minicom tool, which connects to the serial port and is basically a terminal emulator. You install it using the usual sudo apt install minicom, and once it's installed you can do minicom -b 5200, and then the device is dev tty acm0, and this is what it was connected as before, and we saw it earlier. Hit enter, and we've got a terminal prompt. Now the problem, or one of the things to be aware of is that you're not able to use shell commands like you normally use. So for instance, ls is a shell command and that won't work in here. What you have to do is basically put all the instructions in code, and to do an ls you have to import the OS module and then do os.list directory, and that shows us the content of the top level directory. And if you add lib in there, it'll show you the contents of the lib directory. If you want to execute something, then it's a little bit more involved. You have to do exec open the file name and read. So if I just break this down, just notice there's a typo there. So what it's going to do is open the file testpixels.mpy.py, pass it to the read method, which is going to pass that to the exec, and it's going to execute that. And as you can see, that's now running the program. So I've just stopped that using the Control C. To quit out of the minicom, it's Control A, Q. Now another useful tool is the ability to be able to transfer files onto the Arduino. I'll just change into the Arduino Pixels directory first. I'll send one of these files as an example. And that's installed using pip3 install, and it's an adafruit library, adafruit-ampy. Once that's installed, so it's been installed onto my local path. In fact, I think if you do sudo, it'll probably install it. Yeah, so if you run sudo pip3, I think you should just be able to run ampy directly then. Okay. Now we've installed ampy, we can use that to transfer files onto the device. Now, recall that when we saved the updated version of testpixels, we saved that directly onto the Arduino, and that's one of the disadvantages using Thonny, is that you have to make sure you keep a copy locally as well. In this case we haven't done that, so what I'm going to do is just rename the OMV one to MPY, and I'm going to edit that and add the lib part back in. Now for that to be able to run automatically, then we would need it to be called main.py. So what we'll do, we'll transfer main.py to the Arduino, and that's done by doing ampy -- port, then the device, and then put, and then the name of the file. Now we should be able to go into the Arduino using minicom. And we can see we've now got this file called main.py. What's going to happen is when we reset the Arduino, it's going to automatically load and run that. I'll just quit out of here. I'm going to power that off and power on the Arduino, so I'm going to full reset. and the sequence has started running. We can just go on to here and we can see that running through the serial interface as well. We've shown 3 different tools here. One thing to be aware of is to be very careful when you're mixing and matching them. So if you open up a terminal window using the command line, then you're not going to be able to use the terminal and transfer files in, say, using the OpenMV IDE or Thonny. While I was doing some testing on this, I couldn't figure out why OpenMV couldn't connect, and I realised I'd got minicom still running in a minimized window. So that's something to be aware of, as well as just a reminder that if you're using Thonny, make sure you keep a local copy of all the code, because it could be quite frustrating if you do your coding directly on the Arduino and then wipe it off, not realizing you've not got a local copy. There's just a few things to be aware of on that. In summary, I've shown how you can install MicroPython onto the Arduino and program it using either OpenMV, as recommended by Arduino, or the upstream version of MicroPython with the Thonny editor. I did find problems with OpenMV in the Raspberry Pi, but remember this is a brand new version of the OS, so it might be that that will get sorted out fairly soon. I think MicroPython is really good, but one thing to be aware of is the documentation is perhaps not quite as good as the C++ documentation. There is plenty of documentation on MicroPython, but for the specific devices and features of the Arduino RP2040, there's a bit of information on the Arduino website, but there's not many code examples and things like that, and it's quite early days yet. Hopefully that's going to improve over time. Personally, I prefer the Thonny editor to OpenMV, but if you want to the official Arduino version of MicroPython, that's best installed through OpenMV, which also provides the code examples. But you can switch to Thonny for editing the code after that's installed if you want to do that. So I hope you found this useful. I'll be creating more projects using Arduinos and MicroPython in future. So if you have any projects using MicroPython on the Arduino, let me know in the comments. It'd be useful to hear about what other people are doing, and I'll hopefully be adding some more of those later on. If you haven't already subscribed, please do so. Click the bell icon to get notified of my future projects. I look forward to seeing you on a future video. Thanks for watching.